ऑडियो ऑफ कर दूं?
ऑडियो तो ऑफ है।
फिर ये क्यों दिखी तू अभी मुझे?
क्योंकि वीडियो ऑन है।
तो वीडियो भी ऑफ कर दूं? तो साइड से ही ले ले फिर।
ऑडियो ऑफ है कि नहीं? नहीं है।
Om Shri Sai Ram. It gives me a great pleasure to extend a very warm welcome to all participants on behalf of Sri Satya Sai College for Women Bhopal, under whose umbrella we all are together for the international webinar on Supercapacitor, a futuristic energy storage device. I, Arpana Singhal, Assistant Professor from Department of Computer Science and Application, welcome to a dynamic and distinguished personality, Honorable Chairman Dr. Meena Pimpulapure Madam, respected keynote speaker Professor N.K. Gaur Sir, subject expert Dr. Amrita Jain Madam, our collaborator EC member IAPT Dr. P.K. Dubey Sir, respected Principal Dr. Sudha Pathak Madam, Vice Principal Dr. Asha Agrawal Madam, HOD Physics Department Dr. Jyotsna Galgale Madam, Convener Dr. Archana Srivastava Madam, and all the faculty members. Once again, welcome to all of you in this webinar. Now I would like to invite our Principal Dr. Sudha Pathak Madam for delivering the welcome address. Over to Principal Madam.
My humble salutations at the lotus feet of Sri Satya Sai Baba. Sai Ram to everyone and good afternoon to all dignitaries, especially our beloved Chairman Dr. Meena Pimpulapure Madam, distinguished guest speakers, Professor N.K. Gaur, Director, Barkatullah University Institute of Technology, Bhopal, our subject expert today, Dr. Amrita Jain from Institute of Fundamental Technological Research, Warsaw, Poland, Professor P.K. Dubey, EC member, Indian Association of Physics Teachers, IAPT RC09, convener of this international webinar, Dr. Archana Srivastava, and moderator, Mrs. Arpana Singhal, and all my colleagues and dear participants. It is my great pleasure to welcome you all to the international webinar on supercapacitors, a futuristic storage device. It is being organized by the Department of Physics of Sri Satya Sai College of Women, Bhopal, Madhya Pradesh. As we all know that energy is necessary to function and progress in our world, we use energy every day in heating and cooling our homes, lighting office and buildings, driving cars, moving freight, and manufacturing the products we rely on our daily lives. Hence, production and storage of energy is of paramount importance. It is high time that such an event took place to highlight the remarkable contribution which supercapacitors make as a promising storage device in so many areas of our lives. Such webinars have a profound impact on the way we educate our coming generations, and Sri Satya Sai College for Women is pleased to have been a partner in the intellectual growth of our students and the society at large. Our focus on inclusive education, which focus on the all-round development of students from all walks of life. not only academically, but spiritually as well, by striving for excellence in the field of teaching, learning, research, and innovations, and catering to the society through our outreach programs. I would like to give a small introduction of our college. Our college was accredited grade A by NAC, and then we progressed towards autonomous status in 2018. This was made possible by untiring efforts of our staff and guiding leadership of our chairman, Madam Dr. Meena Pimplapure, who is a source of inspiration to all of us. We are proud recipients of DST FIST grant by Department of Science and Technology, Government of India, to uplift the research infrastructure of the college. We have research lab with all modern and sophisticated instruments which cater to the college as well as to the faculty and students of surrounding colleges of Bhopal. Our science department, as well as commerce, computer science, education, law, humanities department are also there, and the faculty of all these departments are also engaged in the field of research of their respective subjects. We have many international and national research publications in UGC recognized journals of high impact factor of our credit every year. I would also like to mention that the Department of Physics is active in the field of research in material science, and convener of this event, Dr. Archana Srivastav. I very proudly take her name that she is also the IQAC coordinator of the college and DST FIST research grant coordinator. And she has made positive efforts in making our institution an autonomous institute. She has more than 55 international research publications to her credit. Her head of the department, Jyotsna Galgale, is also engaged in research work with her. She has presented many research work in USA, Japan, China, and France, along with many national and international conferences in India. The department has completed a UGC minor project under the guidance of Dr. Archana Srivastav. Archana Srivastav is referee of many international journals and international events. Faculty members of this department and the entire science faculty are recipients of many awards, and this physics department is also the recipient of Best Poster Award in International Symposium and other academic careers. I congratulate Dr. Archana Srivastav, convener of the webinar, and Mrs. Arpana Singhal, the moderator of the event, for their efforts and wish them success. I welcome you all again for a meaningful and fruitful session today. I sincerely hope that you will all enjoy today's session. Thanks again for your participation. Saira.
Thank you very much, madam, for your kind words. Now I humbly request to Chairman Dr. Meena Pimpulapure madam to deliver presidential address and her blessings. Over to Chairman madam. मैडम आप अनम्यूट कर लीजिए चेयरमैन मैडम.
Sorry. My humble salutations at the lotus feet of my Guru, Bhagwan Shri Satya Sai Baba, and my parents, my father, eminent physicist, Dr. D.R. Bhavalkar, professor in the University of Sagar, which is now Sir Hari Singh Central University, and my mother, Dr. Vanamala Bhavalkar, a Sanskrit professor in the same university. My humble pranams at their lotus feet. A very good afternoon to the eminent faculty, guests, research scholars, and dear students who have joined us on this afternoon. It is a great privilege for me to address and declare open the first international Supercapacitors webinar and to welcome the participants from all over the world. Today, I will begin my address with a slok from the Holy Bhagavad Gita, written in Sanskrit language thousands of years back. It says, Nayanam chindanti shastrani, nayanam dahati pavakaha, na chayanam kledayam tapo, na shoshayati marutaha. It means no weapon can cut the soul, the Atma, the self, into pieces, nor can it be burned by fire, nor moistened by water, nor withered by fire or by wind. This Atma or soul, what is it? It is nothing but an absolute abstract form of energy. And in common language, we can say that this energy can never be destroyed or created. Such is the importance of energy which the rishis of ancient times knew. And today we have gathered here to reiterate the importance of energy which is required for sustaining life on earth and progress of the mankind. I am humbled when I consider the vastness of this soul or energy which is formless, all pervading, ever present, always new, non-destructible, and it just changes its form from matter to abstract and vice versa. Energy is transformed from one form to another, and this is the basic principle of physics. This webinar, organized by Dr. Archana Srivastav with a team from Department of Physics on physics, and moderator Mrs. Arpana Singhal from Department of Computer Science and Science and Applications will brief us about these energy storage devices. I wish them all the best for this event. Today, our eminent speakers from academia, Professor N.K. Gaur, Director of Bhopal Research and Profession, Dr. Amrita Jain from Poland, have joined us to share their expertise and knowledge on this subject with us. I heartily welcome them. We are honored. I must congratulate the principal, Dr. Sudha Pathak, Vice Principal, Dr. Asha Agrawal, and HOD Physics, Dr. Jyotsna Galgale, for supporting such a knowledge-based webinar. I'm glad to share that Professor P.K. Dubey, EC member of Association of Indian Physics Teachers, and Dr. Uttam Sharmaji, Secretary, IAPT, have collaborated with our organizers. I thank them for their efforts. It's my great pleasure to welcome all the participants of this webinar. I have been told that many participants have joined from almost all countries of the world and also from all states of India to this webinar on supercapacitors. I wish you all have a fruitful session ahead. Obviously, it goes without saying that great efforts went in preparing for this seminar, and because of all the members who have been working hard day and night to shine their performances, I thank them all. I wish them best. I wish team members of this webinar a great success. And I again thank everyone, and I am thankful for getting this opportunity to say a few words in webinar. And all candidates who are going to listen to this will definitely have access to the greater knowledge of this topic and subject. Thank you, and Sai Ram and best wishes. I declare this international webinar open. Sai Ram.
Thank you so much, madam, for your blessings. Now I would like to invite convener of webinar, Dr. Archana Srivastava, madam, to share objective and theme of webinar and introduce our keynote speaker, sir. Over to Archana, madam.
Saira, everyone, and a very good afternoon to everyone here in India. And as it is still morning, late evening, or night in some other parts of the world, so a good day to all of you. As you all join here at the international webinar on supercapacitors, a futuristic energy storage device. And I, Dr. Archana Srivastava, extend my heartfelt gratitude and warm welcome to eminent speakers and delegates who have joined from all over the world. We are indeed honored to have with us about 1,500 participants from almost 20 countries, making this webinar a truly international one. We have two presentations planned for the day, and that will reveal the diversity of these storage devices and their applications while focusing on the current status of research in this area. The presenters today will guide you through the details of the topic and applications in everyday life to fill the gap being felt about the importance of energy, its production and storage. A great physicist and inventor, Nikola Tesla said, "If you want to find the secrets of the universe, think in terms of energy, frequency, and vibrations." And I think the whole physics revolve around energy. So, the theme of this webinar is supercapacitors as they emerge as promising storage devices apart from lithium-ion batteries. And I must mention here that the three inventors of lithium-ion batteries won the Nobel Prize of year 2018. This fact itself proved the importance of energy storage devices in the global scenario. The future candidates down the timeline are many, like semiconductor magnetic energy storage, popularly known as SMES, PEM fuel cells, solid oxide fuel cells, and flexible energy storage devices using nanomaterials. Now, the need of storage system, that is the energy storage system, may be for a pulse of high energy or for a nanoseconds or a prolonged constant supply from a few hours to years, maybe for small devices like our mobile, laptop, etc., or for large energy grid systems like a huge industrial setup or for a nuclear plant. Different techniques and devices are used to match the demand. I can assure you this field has a vast sky to expand and for you to explore. This webinar is just a sneak peek in this area. I would like to take this opportunity to express my deep appreciation for Professor N.K. Gaur, Director, Barkatullah University Institute of Technology, Bhopal, and in charge, Head of the Department of Electronics, Barkatullah University, for honoring us a keynote speech for this webinar. I also wish to give special thanks to Dr. Amrita Jain from Institute of Fundamental Technological Research, Polish Academy of Sciences, Warsaw, England, for taking time to join us on this occasion. This, however, webinar will not be just another talk show. By the end of the event, we intend to hold a question-answer session, and our experts will be glad to answer your queries. I would like to take this opportunity to thank the webinar organizing committee for their diligent work. In closing, I hope that all of you will enjoy the webinar, and I wish our participants will have a very pleasant experience during the webinar. Now, it is with great honor that I may now introduce to you the keynote speaker of this session, Professor N.K. Gaur. Professor N.K. Gaur has obtained his PhD degree from Bhopal University in 1989 and has been a postdoctoral fellow of UGC and DST. Professor Gaur is a recipient of the MP Young Scientist Award 1988 and Career Award UGC 2004. His current research interests are in the physical properties of CMR, that is colossal magnetoresistant material, which are used in memory devices, multiferroic oxides, and intermetallic compounds. He has published over 220 research papers in refereed journals of high impact factor and has more than 1,421 citations. His H index is 20 and I-10 index is 8. He has presented 20 papers in national, international conferences, symposia, and successfully guided 29 PhDs, with 6 pursuing for their doctoral work. He has also delivered many invited talks and chaired the session in national, international conferences, symposia, etc. He has visited many countries for this purpose. He is a referee in many international journals which are listed in Scopus, and he has also successfully completed 8 R&D projects in the university. He was in charge HOD of the University Science Instrumentation Center. Presently, he is an active member of DST Phase 2 program and UGC DAS 3 program. Now, with this small introduction, I invite Professor Gaur for his presentation on the topic. Over to Professor Gaur.
Thank you, Dr. Archana Srivastava. Good afternoon. Chairman, respected Dr. Meena Pimpalapuri, Principal of College, Dr. Sudha Pathak, Vice Principal, and EC member of IAPT, Dr. P.K. Dubey, Head of the Department, Physics Department, Dr. Jyosna Galgale, Dr. Archana Srivastava. Both the Dr. Jyosna Galgale and Dr. Archana Srivastava, they are actively participated in research program and very sincere and dynamic. It can be seen they bought this DST quiz program in undergraduate college, which is very remarkable. And the convener, Dr. Archana Srivastava, and moderator, Dr. Arpana Singhal. So thank you inviting me to deliver the keynote address.
Are you able to share?
Yeah, I am just trying. Just a minute.
सर आई थिंक जूम के बगल में जो पावर पॉइंट दिख रही है, आप उसको जूम के पास अभी आप गए थे, उसके बगल में लेफ्ट हैंड साइड जो आपको पावर पॉइंट दिखी वो क्लिक कीजिए प्लीज। ये रहने दीजिए, इसको मिनिमाइज कर दीजिए सर।
या फाइनल पीपीटी आइकन भी दिख रहा है सर की स्क्रीन पे, शायद वो।
सर ये जूम वाला जो विंडो खोला है आपने, ये तो मिनिमाइज कीजिए, आपका पावर
जी।
पॉइंट करके दिख रहा है, आप उसको क्लिक करें
सर साइड में,
इसके लेफ्ट हैंड साइड। हाँ ये लेफ्ट हैंड साइड सर, नहीं नहीं इस पे, हाँ ये
लेफ्ट हैंड वाला
पावर पॉइंट आइकन बना हुआ है।
ये पी का एक आइकन बना है जूम के बगल में लेफ्ट हैंड साइड, तो आप प्लीज उसे क्लिक करें।
ओके,
नाउ
स्लाइड।
इट्स ओके।
ओके सर, फाइन।
So I am going to present the future energy storage devices. Energy is the present day need globally, and you see the energy, we have the conventional sources of energy like coal, uranium, petroleum. So the energy which cannot be destroyed, and it can be preserved or stored in various form of energy. So now the non-conventional energy, if we see, we have this solar, wind, hydro, and if we see nowadays a lot of work is going on this biomass, in which we get energy from wood, garbage, crops, alcohol, landfill gases, and so on. So if we see the demand globally, we complete the demand of energy from oil, that is 32%, natural gas 22%, coal 28%, nuclear energy that covers 5%, hydro 2%, biofuel based 10%, and others in 1%. So you see the energy storage, there are many form of energy. If we see the mechanical, which is the conventional one, in which we store energy in pumped hydropower, compressed air energy storage, flywheels, and thermal energy in thermoelectric storages. And nowadays, lot of batteries which you use in nowadays in mobile, laptop, iPods. So they are the lithium-ion battery, which is very common used in now gadgets. Lead acid battery, high temperature batteries, flow batteries, hydrogen storage, natural gas storage system, and if we see the electrical, so they are the future storage that covers by the supercapacitor, superconducting magnetic coil. So I am focused on the superconductor magnetic coils, supercapacitor, lithium-ion battery, and you see we all know the conductor. In conductor, you see it passes the current. And in 1911, Kamerlingh and Owens, he discovered that what happens if we cool any metal to a sufficient low temperature. He found a very unique phenomena. He found that suddenly the resistivity, which is going to be decreased, and suddenly it drops to zero. And he got this wonderful phenomena because resistivity is zero, that means conductivity is infinite. So they gave it name as superconductor. And later on in 1933, the Meissner, he has also shown a wonderful phenomena when you see what happens when we pass the magnetic flux through any metal. So the flux can be passed from the metal. But when we make it superconductor by cooling the metal to a sufficient low temperature, when Meissner passed this magnetic flux it will be just excluded by the specimen or it repelled by the bulk of the material. So this is again a very unique phenomena. They Kamerlingh, Owens and Meissner, they got Nobel Prize for this piece of work. Later on, the challenge to physics, you see what happens. We all know that if we bring two charges, same charges, in metal, there are only 3 electrons. So when we bring two charges, two negative electrons, then there should be repulsion. But they found that when it is superconductor, there are only electrons. So they found that there is an energy gap. And if energy gap is there, that means there is the attractive force. And there is no evidence the material which repel each other show the energy gap. But in superconductor, they found that there is energy gap. That means there is attraction between the electrons. So in 1950s to 60s, Bardeen, Cooper, Schrieffer, they pointed out that what happens, the two electrons, they interact via a phonon. So there is a attraction, the two electron via a phonon, or that is a electron phonon electron interaction. And you see, we have done a lot of work and guided almost 10 PhDs on superconductor. The list is given, which we have covered: the superconductor, the europium, barium, manganese, copper oxide, AgO added, LaCaBa2, Cu2O7, and the intermetallic compound MgBu2 and their combinations, and the RCaBu2, Cu3O2, where rare earth is lanthanum, iridium, niobium, europium, and 1,2,3 superconductor, that is YBa2, C3O7. So as I told you, once we make it superconductor, so this is the property of superconductor. What happens if superconductor is there and a magnetic flux which is passing through it, and if we suddenly drop the field, then what happens? The property of superconductor, the magnetic flux cannot pass through it. So if we have the superconducting coil and cool it by the refrigeration system and connect it to the power switching and conditioning as shown in this figure, so we can make the superconducting coil which work as the storage of energy. And there are a lot of advantage of this superconductor for magnetic energy storage. This is an energy storage system that stores energy in the form of DC electricity by passing current through the superconductor, and stores the energy in the form of DC magnetic field. The conductor for carrying the current operates at cryogenic temperature, where it becomes superconductor, and thus it virtually no resistive losses as it produces the magnetic field. The magnetic field is created by flow of direct current through the coil. In this state, the current in a coil can flow for infinite time. This can be seen from the time constant of a coil, that is T is equal to L by R. If R goes to 0, that is in the superconductor. If we take the superconducting coil, so resistance is 0. If resistance is 0, that means T is infinite. And the stored energy is inductive also. E is equal to half, that is half Li square. The benefits of this superconducting coil storage energy that improves power quality for critical loads and provide carryover energy during momentary voltage sags and power outages. Improves load leveling between renewable energy sources, wind, solar, and the transmission and distribution network. Environmentally beneficial as compared to batteries, superconductivity does not rely on chemical reaction, and no toxins are produced in this process because it is not a chemical reaction process. So there is no toxins. Enhances transmission like capacity and performance. SMEs feature a high dynamic range and almost infinite cycling capacity, and energy recovery rate closes to 100%. Ultra high field operation enables long-term storage SMES system in a compact device with cost advantage in material and system cost. Here, it is important that in superconducting coil in which we store energy, you see in the storage, in conventional conventional methods in which we store energy, almost 20 to 30% of energy that lost. And if we use this superconducting coil, there is no loss of energy. Here, I have shown you there are a number of techniques by which we can grow the thick and thin film of superconductor. Here, I have shown you the conventional solid state reaction method by which we can grow the bulk material. So first of all, the stoichiometric, this is the flow chart for the solid state reaction method, in which we take the stoichiometric ratio and weighing it, and then second is grinding. So we grind it up to the atomic level so that they mix up to the atomic level. So we grind it for few hours, and then the mixture put in the crucible and finally placed in the furnace. The temperature depend on the material to material, somewhere around 80 to 1400 degrees centigrade, depends on the compound. So we heat it for 8 hours, sometimes 12 hours, and then this again, what we will do, we calcinize it. Again, we grinded it for few hours, and using the pellet, what we use is hydraulic press and give some ton of pressure and make the pellet of the compound. And again, we put in the furnace, and if we have to blow the oxygen to oxidize the material. So finally, in the high energy ball mill, we put these pellets, and then once we make it, then our first aim to characterize it, whether it is superconductor or not. To check it, we do the characterization. First, we know its structure by using the X-ray diffraction technique, and then we use this other characterization using the vibrating magneto. And you see, I have shown you some of the result. This is by CA BA2 CU307. If you see, we have taken the XRD. Once we confirm that our material is superconductor, the second test is the RT measurement, resistivity temperature measurement. So in resistivity temperature measurement, what we do, if it is superconductor, so at a transition temperature or critical temperature at which this compound, its resistivity suddenly drops to 0. So you say in this case, here it is somewhere around 75 K, at which it shows the superconductivity. So critical temperature for this compound is 75 K. This is again the second compound. This is Na2CaBa2Cu5OZ, in which we have taken the RT measurement, Rietveld fitted X-ray diffraction pattern, and the scanning electron microscope picture. So by making these superconductor can be used as superconducting coil. Now we come to the second storage, which is the future technology to store the energy, that is supercapacitor. We know the capacitor stores the energy very less, and supercapacitor, this is an electrochemical capacitor that has a very high energy density compared to the common capacitor, that is about 100 times more than the capacitor. And it is also known as the double layer capacitor. The capacitor range 100 to 5 kilofarad. The construction of supercapacitor we can see here in the picture. The supercapacitor are constructed with two metal foil, each coated with an electrode material such as activated carbon. The electrodes are kept apart by an permeable membrane or separator used as an insulator to protect the electrode against short circuit. The construction is subsequently rolled or folded into a cylindrical or rectangular shape and packed in an aluminum cage. So the main feature of this supercapacitor, that store high storage, high amount of energy, and it has a high capacitance, high rate of charge and discharge, little degradation over thousands of cycles, low toxicity, high cycle efficiency, and it has a lot of application in the day-to-day life. That is in startup mechanism for automobiles, used in diesel engine, startup in submarine and tanks to run electric vehicles and buses. Tesla, it is going to use these. Tesla is a company in US. It is going to use the supercapacitor as battery in electric buses, backup power system in missile and satellite, power sources for laptop, flash in cameras. Lithium ion battery, which is very common in nowadays, the gadgets we use, you see mobile, laptop, iPads. So these lithium battery is used. And this battery is basically a transducer that converts chemical energy into electrical energy or vice versa. The schematic diagram of lithium ion battery is shown here. It contains an anode as a source, cathode as a sink, and electrolyte for the separation of transport and electronic transport. So cathode material can be used as LiCOO2, LiMn2O4, LiNiO2, LiFeO4, and anode material, the graphite, hard carbon, and electrolytes are LiPF6 in carbonate solvents. The advantage of lithium ion battery, it is very light weight as compared to other batteries, and it has high energy density potential for yet higher capacitor. You know what happens? Lithium is very reactive. So the energy storage that is in the atomic bond of this lithium, and it does not need the prolonged priming when new one regular charge is all that needed. Relatively low self-discharge. Self-discharge is less than half of the nickel-based batteries. Low maintenance, no periodic discharge is needed. There is no memory. Especially, cell can provide very high current to applications such as power tools. It has some limitation also, requires protection circuit to maintain voltage and current within safe limits, subject to aging, even if not in use. Storage in cool place at 40% charge reduce the aging effect. Transportation restriction, shipment of larger quantity may be subject to a regulatory control. Restriction does not apply. Expensive to manufacturer, about 40% higher in cost than nickel cadmium. Not fully mature, metal and chemical are changing on a continuing basis. So in this sequence, the lithium ion battery, which is used in nowadays in most of the mobile laptop, the lithium can be replaced by the sodium also. So the work is going on, and some of the R&D organization, they have started to work on graphene batteries. That means the carbon batteries. Now the energy storage in the lithium-ion batteries. So we have also fabricated few material, this pi-SrMnO3, some oxide material. This is GdMn1 - XCrXO3, HOGdMnO3, Europium strontium manganese oxide, BiMn2O5, W-doped Ca3MnO4, Mn4O10, and Europium FeCO3. These compounds are also used for energy storage, and work is going on. And these are the material which we have fabricated in our lab. And the reed weld fitted XRD for Bi2Mn and IU6 we synthesized in our lab. We have shown some of the results. The first picture that shows the reed weld fitted X-ray diffraction. In second figure, it is XPS. And in third, we have plotted the binding energy with the intensity and the permittivity. We have plotted in one of the picture, loss tangent and Nyquist plot. We have also shown in the picture. So you see the future energy storage, the superconductive coil, lithium-ion battery, supercapacitor. These are nowadays the need of day-to-day life, and the research work is going on, and we hope the storage capacity will be more as compared to the earlier one, conventional one. And finally, these are the publication which we have published. All these materials, they are used either in superconducting coils, and the oxide materials they used as the supercapacitor. So these are the publication, and thank you very much for your attention.
चलो एक बार देख लें। Thank you so much, sir, for such an excellent presentation. Your lecture was quite informative and gave us more information about subject. Now I would like to invite Dr. Archana Srivastava Madam to introduce our subject expert, Dr. Amrita Jain Madam. Over to Archana Madam.
Thank you, Arpana. Now, it is indeed a pleasure to introduce the subject expert of today's webinar, Dr. Amrita Jain, working in Division of Advanced Composite Materials, Institute of Fundamental Technological Research, Polish Academy of Sciences, Poland. She is working in the field of energy storage devices and involved in the development of electrode and electrolyte materials for batteries and supercapacitor application for more than 10 years. She is involved in the synthesis of carbonaceous material extracted from biomass, carbon nanotubes, graphene, polymeric materials and its composites, ion liquid-based solid electrolytes, etc. A bright student throughout her career, she did her PhD from JP University of Engineering and Technology, India, and her thesis is notified in Poland as well. She is recipient of Young Scientist Award, and other international research fellowships. She was in teaching profession prior to joining this institute. She has co-authored 2 books on supercapacitors and biomass-based carbon and its application, and 1 monograph is to her credit. She has many publications in international journals and has citation index of 186 and H index 8. She has delivered many invited talks in international symposiums and conferences. It is indeed an honor to listen to Dr. Amrita Jain on her topic of research. So over to Dr. Amrita Jain.
Thank you so much. Today in this world, we are on this planet, almost 8 billion people will live on this planet. And believe us, believe me, every second, everyone is using energy in every part of their life. Imagine a day without energy. What does our planet look like? A mere black thing. So if such kind of thing like energy, if it is that important, then definitely its development, it should be on the top priority. I, myself, Dr. Amrita Jain, I'm so happy, and of course, it gives me an immense pleasure to present myself, to talk with all of you on this platform on the topic supercapacitors, a futuristic energy storage devices, on which I'm working from over 10 years now. I'm really thankful to the organizers, Sri Sathya Sai College of Women, Bhopal, to the principal, chairperson, convener, and to everyone to give me this opportunity to talk about this on this platform. Imagine if you can charge your mobile phone in few minutes, in a matter of couple of minutes. Imagine you are driving to some luxurious trip without even waiting for a few hours to charge your car. You can charge your laptops in few minutes. All these things are certainly possible, certainly. And all these things need development. In this world, now we cannot wait for years and years, for let's say 20, 30 years to develop something. No, we have to start today and right now to develop energy. My talk of the today is divided into following subtopics. Definitely going to introduce all of you about supercapacitors, its types, the very famous question, supercapacitor versus battery, what is the difference? Why supercapacitors? This interesting device certainly results from my experimental work, conclusions, and some future perspectives of this amazing device. Always people ask me how I ended up working with this. So 10 years before, when I entered in the lab, I was really confused. I had no idea. I had heard first time in my life about supercapacitor. And when I read, I was like, yes, I want to develop this. And so I did. Now, if we are talking about energy, then what is the need? And if there is a need, certainly there is a solution. So the scientific progress, high-tech development, and worldwide commercialization are leading us to an energy and environmental crisis. which is prevailing globally. In one of the talk by Nobel laureate Professor Richard, he told that energy is going to be the biggest challenge in the next century. And if this is the situation, certainly it is very high time to store this energy. Our world, our planet is full of renewable energy, wind, solar, turbine, many things. We just need to store it. We need to find some solution to store this. And this is what we are working on. If this is the situation, what is the solution for this crisis? One of the solution can be the development of electrochemical energy storage devices, which has a real wide applications in every scenario. We need energy everywhere, even not only human being, even to maintain everything. We need this energy. And nowadays we need everything like quick, in a flash of second. No one wants to wait. Look at your phones. You always want to select a phone whose charging is super fast and whose discharging time is as long as possible, because we do not want to wait. Going further, let me step back a little bit before introducing to this world of supercapacitor. I want to step back and wanted to go back in a bit throwback of the basic physics. The capacitor, the supercapacitor word derives from the word capacitor. So what is a capacitor? In the simplest term, it is the measurement of the ability to store electric charge, calculated by the simplest formula C is equals to Q by delta V. I think I remember that I read somewhere in my grade 12, or maybe nowadays kids are learning even earlier. And we have taken the simple concept of that to develop this device to the next level. Once again, the very simple and the basic form of capacitor is the parallel plate capacitor. And for this capacitor, the capacitance can be calculated by using simple formula. Kc is equals to epsilon naught A by D. Epsilon naught A is the permittivity, A, area of the electrodes, D, the distance between the electrode. And that's how we are just going to play with these two parameters to find something new. Yes. And while studying about this capacitor, we also have calculated the energy stored. And the energy of this capacitor can be calculated by using the formula U is equals to 1 by 2 CV square, half CV square. C is the capacitance value obtained from the previous formulas. V is the voltage applied between the electrodes. And this is essentially became the energy storage which is stored in the capacitor. Wait, if we are talking about so much of capacitor, electrodes, then there are one interesting thing in between them called dielectric. Now, what are dielectrics? An interesting thing. We should just place in between two electrodes, and the main role is to stop those two electrodes to interact with each other. Else what we will have? A short circuiting. That's it. So what we need is to just protect them from interacting with each other. And there is a limitation of the voltage. It cannot conduct electricity. But wait, what if we exceed the voltage value? Then there is a one term called dielectric background. breakdown. I'm sorry, breakdown. What is dielectric breakdown? One interesting situation where when we overpass the voltage criteria, then it started become conducting in nature. And this is the case of dielectric background. And now this is what we use the concept to introduce in the electrolyte material, the material which can give us some ions. Now, so the last thing on this throwback, that what is the conclusion? Conclusion to this capacitance thing is a simple formula, which is C is equals to epsilon naught A by D, which I just talked a few seconds before. If anyone can see this simple formula, a simple mathematics is applied. That if you want to increase the capacitance, what can be done? Simple, increase the area, decrease the distance. Increase the area of electrode and decrease the distance between the electrodes. But when we do this thing in capacitor, there are certain limitations. You know, there is a section in class grade 12 book, a small paragraph, that what if you want to achieve a value of 1 farad capacitance value, what is the calculation you need? Then you need an electrode with the area of, you know, something like in kilometers separated by certain distance. Imagine, oh my God, I cannot even imagine a big device like that nowadays, where we are moving towards the micro miniaturization. So in this, what we do, because imagine two small things, you cannot make them so close to each other. No, you have to keep them at certain distance. And that's what I'm going to talk about today. How to do this, how to achieve this. And that's what we did in supercapacitor. We increased the area to a tremendous amount and decreased the distance to the minimum as possible. Moving further, the capacitor, the conventional capacitor, is divided into 3 types. The capacitor is divided into 3 types. One is conventional capacitor, electrolytic capacitor, and electrochemical capacitor. And the simplest, you know, definition of capacitor is that they are the fundamental electrical circuit elements which act as a passive element. It helps to store electrical energy, and energy is stored in microfarads. Please mark here, the energy is stored in microfarads in case of capacitor. So to reach to the level of farad is a beyond thing, at least in terms of capacitor. So let's go further to check what can be done. Little bit more about 3 kinds of capacitors. So this conventional capacitor is the basic capacitor in which the mica, paper, ceramic is sandwiched in between the 2 metallic electrodes, which are electronically conducting in nature. Energy is stored by the removal of charge carriers, and the charge separation creates a potential difference between the 2 plates. The second type, which is electrolytic capacitor, further divided into 2 types, tantalum electrolytic and aluminium electrolytic capacitor. Their division is based on the type of electrolyte material used. So for instance, in tantalum electrolyte, there are 2 possibilities to use electrolyte. One is the wet one, second is the solid electrolyte material. In terms of wet, there are a few standard ones, for example, sulfuric acids, or so acidic, basic, or the neutral ones, or solid electrolytic. The standard one used is MnO2, manganese oxide is electrolytic material. In terms of aluminium electrolytic, again divided onto the, again again, it is defined as the type of electrolyte material used. So organic solid membrane is used there as a solid electrolyte material. And the third one is supercapacitors, also called electrochemical capacitor. In this, the electrolyte material is sandwiched between the two electrode material. It can be any. It can be wet, it can be solid. Of course, world is moving towards the solid one because we wanted to be high-tech. We wanted to wear the smart gadgets. And for that, we need solid things. We need flexible materials. Now, supercapacitors. So the definition, just a moment, definition, it is a very unique and versatile energy storage devices which has following characteristics. For example, larger value of capacitance, as in our previous talk. Professor Gaur has also discussed about the similar things, that it is the device which has a capacity to store a large amount of capacitance, almost 20 to 2000 times. It has an ability to achieve greater density as compared to conventional capacitor, and certainly higher power density as compared to batteries. So somewhere or other, it is stuck in between. So we have let's say we have two sides, one a capacitor, on the other side a battery, and supercapacitor somewhere or other lie in the between. That it has a good energy density as compared. So we have actually increased the energy density, which is requirement. And second, that of course we have achieved higher power density, which is lacking in terms of batteries. In a few minutes, in a few seconds after, I'll tell you the basic difference between the power density and the energy density. What does it mean in the simplest term? Electrochemical capacitors are potentially versatile solution to the variety of upcoming energy applications, which are based on their ability to attain a wide energy and power density. And as I mentioned, its power densities is greater than battery, energy densities are greater than conventional capacitors. This is a basic diagram that you can see on my screen of a capacitor. So as you can see, there are two electrode materials and an electrolyte material sandwiched in between. And believe me, these three things do wonders. You just need to play with it correctly and rightly. And these materials do wonders. Okay. So moving further, where are these supercapacitors applicable? What are the, not applications, but certainly where can we use this device? Supercapacitors. Applications which require very high reliability backup solution, power solutions. Then if there is a quick transfer from 1 to 60 seconds of transfer from secondary source to orderly shutdown, because it has a very good power capacity. So wherever you need an impulsive thing, you can certainly call supercapacitors for that. Then power quality ride through to compensate for momentary severe voltage sags, and power buffer for large momentary inrush or power surges. As I was mentioning a few seconds before, that I'm going to tell you the simplest way to define the energy and power density. As you can see from the picture, and I think it's pretty much clear, that all of a sudden a big source of thing is power, and the constant supply is density, energy density. And that's what we are now working on as well, to achieve a good energy density in terms of for supercapacitor. Application model. So as we can see in the picture, that for example, there are two types. One, peak power demand. And imagine in your life also, you always face two situations where you need something continuous to go on, or sometimes you need a peak power thing. So when you are even riding your car, right? You always face two situations. One, you need a continuous power, and all of a sudden there is a hill and you go up and you need a power for that. So in these two applications, we need devices. For the first case, in terms of peak power demand, we need an energy storage devices called ultracapacitor or supercapacitors. But for continuous power, certainly batteries have no other. I mean, these are the best ones. That for continuous power, you can certainly rely on batteries. But wherever you need a peak, you need this device, supercapacitor. And that's why they are complementary to each other. Certainly, whenever this charging needed for ultracapacitor, we need a battery source to get it charged for sure. But its charging capacity is much faster. In a moment of few minutes, you can do that. Now, moving forward with the lecture, let's little bit differentiate between these two devices, battery and supercapacitors. So with the picture, you can see that the first is the primary energy source, that is battery. The second is ultracapacitor. Of course, the discharging time and the charging time for this discharging time is quite higher. Recharging time is also quite higher. You need a good time to charge it, good time to recharge it. But in case of ultracapacitor, it's completely opposite. It needs a less time to charge because again, it all depends on the power density, because the application for ultracapacitor is in power sector, primarily, at least for now. So we definitely, that's why the discharging time is also less, and definitely the charging time is also very less. So I'm going to compare these two devices with few headings. Let's say in terms of charge storage. As you can see on my screen, there is a plot, which is a very famous plot called Ragon plot. This Ragon plot is always plotted between energy and power, energy density and power density. So the plot between energy density and power density is a Ragon plot. And here you can see that it is a standard plot. And here you can see that there are few energy storage devices, batteries and capacitor. And as you can see, the electrochemical capacitor is somewhere or other capped, and at the very left corner you can see the capacitor. So as I was mentioning few minutes before, that the supercapacitor, it lies in between the capacitor and the battery. So again, in Ragon plot, the battery and supercapacitors are next to each other, which are of course advantageous in terms of energy and power density. Where in case of battery, there is a chemical reaction taking place. This is the one major difference, that in case of battery, there is a chemical reaction which takes place. The reactions are called Faradic redox reactions. And that's why after certain time, after certain cycle, you can see your battery is dead. What happens? Because the chemical is finished. Because chemical has a lifetime, a limited lifetime. So maybe let's say after depending on the quality of your battery, but after 500 cycles, after 1000 cycles, it started getting fed. And for instance, even in case of your mobile phone, you have seen this, right? That when we buy a new mobile phone, the performance of battery is excellent. You just need to charge it one time and, it will go for full day and on. And over the time, gradually, it has a short lifetime because it works on the principle of Faradic redox reactions. But in case of the supercapacitor, there is a non-Faradic reactions taking place. Ideally, no chemical reaction. So at the interface, the electrodes, the ions are going in, coming out, going in, coming out. So not practically, but theoretically, see, there's a huge difference between the theoretical calculations and the practical calculations. But theoretically, if we can see in this scenario, then there should be unlimited life cycling. It has a robust cycling in case of supercapacitor. But certainly, when we come to the ground reality, it is not unlimited, but certainly very, very high, let's say 100,000 times as compared to battery. So at least you can discharge it 100,000 times minimum. But in case of battery, you can maximum, again, depend on the type of things you are using, but it is maximum 1,000, 2,000, and that's it. There is a comparison chart on my screen that you can see that what is the discharging time, charging time of battery, capacitor, and electrocapacitor. So let's see. For example, the charging time in case of battery, it takes 1 to 5 hours. In case of capacitor, 10 to the power minus 3 to 10 to the power minus 6 seconds. And in case of electrochemical capacitor, merely 30 seconds. So, but of course, this device, I would not say that it is completely into the research level. No, we have achieved a lot higher. This device have been achieved a lot higher. There are now many established companies. There are many things moved on supercapacitor technology, but still many work to go to it. The second type is the potential profile. Now, this is quite interesting difference. Imagine a situation where you are riding, for example, you have a battery, and I'm sure you have seen that every battery has a voltage written at the back of it. That, okay, 0 to 3 volt, 0 to 5 volt, 0 to 1 volt, whatever. So let's say we have a battery of 5 volt. In case of battery, you can draw two things, 0 volt or 5 volt. We cannot draw any voltage in between. You can draw either 0 volt, so it has kind of a constant thing. You can draw 0 or you can draw 5. That's it. Nothing in between. But in case of supercapacitor, you can draw any same situation. Let's say 5 volt. Okay, so you can draw any voltage from 0 to 5. So in case of supercapacitor, voltage gradually decreases due to the removal of charge at the interface. In case of battery, it remains constant throughout the process of thermodynamic reasons. Area under the QV curve denotes the energy density, and this is the reason, and from graph also we can see that it has lower energy density as compared to batteries. But certainly then the other side also, that battery has low power densities as compared to supercaps. In terms of configuration also, the difference is in case of battery, we have two active electrodes, anode, cathode. I'm sorry, there is some, I think, typing mistake, but this cathode should go under the active electrode, and electrolyte is sandwiched in between two. Supercapacitor, we have two blocking electrode or two active electrode, and electrolyte is again in between. We need it. Otherwise, they will again start fighting with each other. So we do not want that for sure. The performance characteristics of supercapacitor, it is in a midway in between conventional capacitors and batteries. It has fast charging and fast discharging capabilities, very reversible process, almost 100 and 1,000 times you can go. The same, lower energy than battery and greater energy than capacitor, and it has very good, excellent low temperature performances. One of my very good friend owns an industry for supercapacitor, and they have been invited by the DRDO of India. And he was sharing me a very good incident that they were invited by this DRDO, and they said that, can you please help us to switch on this Arjuna tank of India? And they were like, really? And of course, Arjuna tank is the big one. And the problem is that see, what is the problem and what is the interesting practical thing? For example, we often face a problem of a battery dead of our car during the time of winters. And so, all of a sudden you want to go somewhere, you switched on your car and you see, and then that's it. Your battery is dead. It needs charging. Now here, if you have supercapacitor, it will charge your battery in a second. And then what is the concept? If the battery is once started, and if your car is going on, that the battery recharges itself, right? You need that impulsive power to switch on the thing. And for that, we need this magical device. So really, the defense, for example, the defense sector, not only India, everywhere, right? They are facing such kind of situations because their defense trucks, let's say, or their defense tanks are parked somewhere in the range of -50°C, or maybe even less, sometimes -55 or something, or sometimes they are in some very deserted area of over 55°C. So they need an impulsive power to start up. And that what is this device can be useful of, and it is there to start the locomotives of the engine in the train. And for this, okay, maybe in few seconds when I'll talk about the application, maybe we can talk a little bit more about it. So applications and the world market. It's quite easy to remember the applications. You just have to remember the word items. Industry, transportation, energy, and some more applications. In terms of industry, automotive, Yep. So in terms of industry, in a sector like automation, to lift automation, for example, robotics, other factory, to provide the power boost, backups for forklifts, crans, electric carts, fuel cell systems, some regenerative braking. For example, let me take an example of New Delhi, where this metro station, they are successfully using this regenerative braking, a capture of energy. So when you actually put the brake, you can store the energy. So in this situation, this device works like wonder. The second application, and UPS, for example, transportation. Very commonly, we can see nowadays hybrid electrical vehicles. For instance, me myself using HEV car, engine starting, regenerative braking, fuel cell support, trains, and that's what I was talking about few seconds before. That to start the engine locomotive, you need a big power. And you know what? For that, you need a big battery. Trust me, a big battery. And this big battery is only because we need to switch on it. And that's why we need see, what's that? You require a power. Battery is lacking of power. Okay, so to get more power, you need a big battery. So what we can do, we can just replace this supercapacitor there in parallel to each other. So when to switch on, you can just use the supercapacitor and then it will switch itself to battery. And that's how we can reduce the battery sizes and hence the weight of the engine for sure. Excuse me. Thank you. Third is the green energy. As in the opening of my talk, I was telling you about the scenario. Come on, green energy, we have surplus energy, surplus. If somehow we have managed to store this solar energy for one day, it is sufficient for a big amount. Wind, solar, wind turbines, solar panels, wave energy, all these things, what you need is to store the energy. And this device can be useful for. More applications include military, medical, smart grid applications, and commercial cooking equipments. Few more applications, for instance, recently in Japan, for instance, they have, for example, in some fairs or in some, some small, the buggy cars, the small, the buses, they are completely turned them into the hybrid ones. They're not using, they're just recharging it, so it acts as a good power source. In video recorders, TV satellite can be used as pulse power, can be used in different kind of toys because of its very long cycling and very high power density, in photo video cameras, solar power generators, etc. So as Professor Gaur also mentioned, that nowadays it has been started using in the car. For instance, recently Honda Civic car hybrid, they started using supercapacitors. So this is basically, see the figure, you can see the combination supercapacitor, battery, controller, and motor. So what can be done? It can be used in parallel to each other. So wherever we need an impulsive power, it automatically switched to supercapacitors, and wherever we need a continuous power, it moved on to battery. Interesting thing. Not for that. If for the music lovers, to go to the very high pitch to match the frequency, supercapacitors are very useful. But of course, it is costly. But in the high range cars nowadays, they started using supercapacitors to give you a good experience for music. A world market says that it is used in mainly three forums: consumer products, industrial, and transportation. Consumer, the day-to-day things: cameras, PDAs, toys, memory backups. In industries, as I mentioned, UPS, windmills, stationary fuel cell, automation, etc. And in terms of transportation, hybrid buses, engine starting, light hybrid, some local power, rail locomotives, etc. Now let's go ahead and talk about the types of supercapacitor, also called taxonomy of supercapacitors. Supercapacitors are of three types rather. So the two main type is one is the electrochemical double layer capacitors, and second is the pseudo capacitors. In double layer capacitors, I mean, in both the capacitor, their charge storage mechanism is completely different. In case of double layer capacitance, storage of the electrical energy is achieved by separation of charges in Helmholtz layer at the electrode-electrolyte interface. Charge separation is static, and the distance in the double layer is of the order of few angstroms. In case of pseudo-capacitance, the electrical energy is achieved by some redox reaction, and there are some electrosorption reaction takes place at the surface of electrode material by specifically absorbed ions that results in a reversible Faradic charge transfer on the electrode. Now, so this was basically, this bifurcation was on the basis of storage principle. The second bifurcation comes in terms of designing of the capacitor. So it is of three types: double layer, pseudo capacitors, and hybrid capacitors. I'm going to talk about a little bit more about it. You can see the flow diagram. Supercapacitors of three types: EDLCs, hybrid, and redox. And then I'm going to discuss a bit more in my next few slides. Okay, so in electrochemical double layer capacitors, what happens? That when the solid material is charged, what happens? Simple thing. Oppositely charged ions from the solutions are attracted towards its interfaces, thereby forming a dense absorbed layer known as stern layer. Because of this surface layer, a diffused layer of ions are also formed in order to completely balance on either side. And this layer so formed is called diffused layer. These two layers in combination, it gives rise to interfacial double layer, which is capable in storing the electrostatic charges. Amount stored can be calculated by using the formula delta Q by delta V. The second type, which is redox capacitors, also called as pseudo-capacitors, it has entirely different charge storage mechanism. In this case, fast Faradic charge transfer reactions takes place, a pseudo reactions, kind of a fictitious reactions, very fast. And then the type of electrochemical process are used in developing redox capacitors can be surface absorption and chemisorption of ions, redox reactions that include ions from the electrolyte, doping and undoping of active electrodes. Of course, these two are complementary to each other. The third and interesting type of capacitor are hybrid capacitors. Hybrid capacitors are one of the emerging class of supercapacitor, which combine two different kind of electrode. So what can be done? So what can be done is that we can have a combination of electrodes. So first case, let's have the same one. Second case, let's have the composite. Now, when I talk about this composite, n number of possibilities are there, right? For example, you can have one type carbon types, one type redox type. Second possibility, one type battery, one type battery, one type carbon, or maybe third type. In battery type, you can have two type of electrodes which are kind of battery types. Or third, interesting and the most emerging one are Super-Ca battery. So in which you can have an asymmetric combination of battery type and capacitor type. You know why? Again, because our motto is to increase the energy density. Our motto is to have one device which has good energy density and of course good power densities. If we are talking so much about electrode materials, let's little bit talk about it. What can we expect as an electrode material? What materials can be used? So in case of electrochemical double layer capacitor, any kind of carbonious material which has very high surface area, very high conductivity, high electrochemical stability, and very developed porosity. Some of the materials are activated carbon, CNTs, graphene, carbon aerogel, zerogel, carbon fibers, etc. can be used for this purpose. Again, if I go back to the properties, remember my very first beginning slides when I told you we need a high surface area electrode. So we need a good surface area. Certainly we need high conductivity. We need good porosity so that ions can go in, come out, go in and come out. And for sure, it should be stable in a normal ambient, not just normal, but at least in the working environment. When I talk about redox capacitors, mostly noble metal oxides can be used. Nowadays, MXenes, very emerging material, first founded by Professor Gogotsoy in collaboration with few more professors in year 2011, and few conducting polymers like polyaniline, polypyrrole, polythiophene, PDOTs, etc. These conducting polymers have a specific property. These are electronically conducting. These are few polymers which are very good and electronically conducting, which we need. In case of hybrid capacitors, again, same, you need a hybrid combination. So what are possibilities? Pseudocapacitive metal oxide with carbon electrode, or lithium metal with some carbon electrode. Essential thing, not just electrode. The second main part is electrolyte. We need to be very much careful about what electrolyte material we are choosing, because you remember the first formula, U is equals to half CV square, where C is okay, fine, capacitance, but V is what? The voltage. And voltage we get from the electrolyte material. So imagine such a crucial factor. You need to select a good electrolyte material which has good potential window. Electrolyte is a substance that contains free ions which act as electrically conductive medium throughout the diffusion of ionic charge. They certainly have few properties. We look for few properties while selecting some material. Let's say low toxicity, safe handling, high ionic conductivity, economically feasible, most important thing, low solubility of electrolyte materials, conductive additives binder, low melting, high boiling point, good chemical stability against the decomposition at electrode surface. So you can see the picture there. This is the one electrolyte. This is a gel polymer electrolyte. I always work on such kind of polymer materials, which are freestanding materials. Rather, and I would say mechanically stable materials too. Usually don't work with the liquid electrolytes because of its obvious drawbacks, like it is so difficult to handle, leakage problems, etc. Some current issues. For example, if we wanted to increase the specific capacitance, what can be done? One, to increase the porosity in case of double layer. And in case of pseudo-capacitance, increase the redox activity. Fast switching on, fast reactions. If you have fast reactions, then you have higher capacitance. If you have good porosity, you have good capacitance. In case of specific energy, what can be done? As I mentioned you in few minutes before, energy can be calculated as E is equals to half CV square by effective mass. So if we wanted to increase the energy density, so what electrolyte material can do for us? If we increase the capacitance from electrolyte material, what we can expect to have a good voltage range. To improve the specific power, the formula to calculate the specific power is P is equals to V square by 4 mR. M is the loading mass of the electrode, R is the resistance. So what should we do to increase this power is to have less resistive components, and of course the rate capability should be higher, and certainly again the voltage. You see, so to increase the specific energy and power density, we need a good electrolyte with good potential difference, but with good potential range. Its potential window should be good. Excuse me. Thank you. Now to improvement, that what can be done. So there are certain various approaches. The first approach is to have an electrolyte material, any type, liquid, solid, polymer, and one side a carbon type electrode, other side a conductive polymer electrode. Make sure to have this electrolyte with a wide potential range. Second approach, one side a capacitive cathode, the other side a electrolytic capacitor anode, and then an electrolyte, of course, with a wide range. Third approach, carbon or redox material or some kind of conducting polymer, or the other side can be battery electrode, of course, sandwiched between electrolyte material. So energy density can be enhanced by increasing the energetically useful charge by combination of supercapacitor electrode with rechargeable battery type electrode. This is the most advanced stage capacitor, but it is not easy to do this combination. Looks quite easy, but it's not easy to find the fit materials which play together. But if we find a good material, then we will be able to achieve good energy and good power density, certainly. Few specific issues which are associated with EDLCs are electrochemical double layer capacitors. Now, this is something interesting that you can see. This is one side is the normalized capacitance, and this side is the average pore size in case of nanometer. There are three regions: region 1, region 2, region 3. In region 1, we can say that the pores are good, substantially larger than twice the size of solvated ions. There was a contribution of capacitance from compact layer on the ions at the walls. So a proper normal reactions taking place. When we go to region 2, then you can see that there is all of a sudden there is a abnormality results, that there is all of a sudden there is a capacitance value which shooted up. And it was an interesting study carried out by J. Shimola et al. In 2006, where they have introduced that at certain nanometer levels, for example, in this case, at 1 nanometer, we got an exceptionally high capacitance value. It might be because of a perfect switching in and switching out of ions. So we need to be careful that the compatibility of electrode material and the electrolyte material, compatibility in terms of their ionic sizes matters a lot. Now, few issues which are related with the electrolyte materials is the very well known disadvantages. Like if you talk about liquid electrolytes, then there is a corrosion problem, self-discharge, lower density, bulky design, transportation problems, explosion problems, many problems like that. So one solution for all these things is to have a gel stable polymer electrolyte, which has a conductivity almost equal to liquid electrolyte, and its potential difference is far higher as compared to liquid electrolytes. In case of liquid electrolyte, you can achieve maximum up to 1 volt or something. But in case of gel polymer electrolyte with certain chemicals, we have also achieved up to 4 volts, which is very high, really very high. Now, few of my experimental results, it's already published in a journal of solid-state electrochemistry. So my work basically is on, so it's an interesting thing that I started my work with the redox supercapacitors, and I started working with the conducting polymer materials. But then I started developing my interest towards using the waste material, converting the super waste material into reusable material, which are suitable for this application. The results which I'm going to show you are the eucalyptus leaves. One quite popular thing available everywhere, at least available everywhere in India. You can find an ample number of eucalyptus trees. So it is a very highly utilizable material, widely planted hardwood in the world, almost 18 million hectares in 90 countries, because of their fast growth rate, great availability, and renewable nature. Carbonization of these leaves results in a 3D eucalyptus carbon with a hierarchical porous structure, which can provide an appreciable high surface area, very good conductivity, good connected and ordered microstructure pores, which facilitate the ion transport easily. So in this study, we have synthesized carbon materials from eucalyptus as an electrode material for EDLC applications. For electrolyte, we have synthesized nanogel polymer electrolyte using PVDF HFP. PVDF HFP is one of the very common polymer used, polyvinylidene difluoride hexafluoropropylene, PC, propylene carbonate, MgClO4 is magnesium perchlorate. We are not using, even till now, I am not using any lithium-based salt because it has really, it is not easy to work with lithium. It is not safe. to work with lithium. I know the performance is very good, but it is definitely not easy to go with. So that's why we are mainly working on magnesium salts, magnesium and lithium, and we are getting almost comparable results. So we are developing material, we are developing our cells using magnesium salts and SiO2 silicon oxide as a nanofilm. For synthesis of activated carbon, charcoal from eucalyptus leaves, we have used chemical activation, and I have used potassium hydroxide as an activating agent. The electrode material was synthesized by using chemical activation technique. The electrodes were prepared by taking the carbon cloth as a substrate material. So this device was completely flexible in nature, because this was a fabric and you can actually bend this device like this. Characterization of the electrodes was carried out by using the standard methods like SEM, which is scanning electron microscopy, BET surface area analysis. Surface area analysis was used to carry out the surface area of the electrode materials, of the synthesized materials. So this is an electrochemical characterization. This is the device which I have used in India. This work was carried out in India. So this was the device which I have used to carry out my electrochemical measurements. In case of electrochemical measurements for cell characterization, few standard techniques like impedance analysis, charge discharge technique, linear sweep voltammetry has been used. Now these are the SEM results. This is the BET studies, and remarkably, as you can see, I have achieved 841 meters square per gram of surface area. Few XRD results, I'm not going into details. Then impedance spectroscopy plots, and the capacitance value is as high as 434.6 millifarad per centimeter square, equivalent to 289.7 farad per gram. Complex power and analysis, CV studies. This is cyclic voltammetry, and this is the cyclic number. We have performed 5,000 cycles. Charge discharge measurements. So similarly, I have used many biomasses like bagasse, coconut shell, almond shells, some drumsticks, and still I am using few. Can't share because the results are still not published, is under work. So these are all the waste material, and we have achieved really nice results from that. So what are the benefits? Certainly the same, that we can get unlimited life cycle, can be cycled for millions of times, good power densities, but certainly there are certain works to be done. For example, we should increase the specific energy, self-discharge time, low cell voltage, etc. Conclusions, that it is a good, interesting device, but for sure, it still needs a lot of work to be done to develop these devices. And these are the future scopes. So thank you so much for giving me an opportunity to talk about this material. Thank you so much once again.
Thank you so much, madam, for such a wonderful presentation. Definitely our participants will get benefited by your expert talk on supercapacitor. Now we need to make some important announcement. Link of feedback form is being provided in chat box and comment box of YouTube video. Please fill it and give your valuable feedback. All the participants put your full name and organization name correctly, as it will get printed on your certificates. We already have few questions. Please ask any question in chat box or comment box. Now, I want to invite Srimati Chhaya Makhijani and Dr. Romsha Sharma from Department of Computer Science for question answer session. Over to Chhaya madam.
Thank you so much, Arpana. Very informative session. Thank you so much.
Thank you so much.
Participant. One of our participants, Muhammad Amir, have a query. Could you please suggest any other potential materials that can be used in energy storage devices?
Potential materials as in electrode materials, as in electrolyte material. For example, as I mentioned in my presentation, that depending on the type of device you want to develop, for example, if you want to develop EDLCs, then you can have some kind of carbonate materials as an electrode material. And if you want to develop a redox capacitor, you can use certain kind of metal oxides, certain kind of electronically conducting polymers for your electrode material. In case of selection of electrolyte material, make sure that you should select some material with good potential values.
Thank you, ma'am. Romsha?
One of our participant, Palashi Gupta, is asking, ma'am, instead of batteries, could we only prefer supercapacitors?
Rather not. We have not reached to that level that we can do that. So it can be better to be used both in parallel to each other.
Thank you, ma'am. Hi, ma'am. Any more questions? One more question from Ananya Kumar, ma'am. Which type of capacitors is used in DRAM?
See, depending upon, I cannot say that which kind of rather capacitor, but I would rather say that depending upon your voltage requirement, depending upon your requirement, you can select like what is your capacitor requirement, right? If you the value of what capacitance you need. For example, if you need something for the peak power, use such kind of capacitor. So depending, I would, it's so, a broad form to us that what can be. So I would rather say that depending upon your needs and requirements, we certainly we can certainly one can select the capacitor available from the various ranges.
Okay, ma'am. Thank you. One more question is there, ma'am. Can we replace Li with any other material to get better results?
See, Li can be, okay, of course, Li is a very established material, but it has certain disadvantages for sure. For example, explosion. We have heard many cases about lithium explosion, right? We are talking on phone and all of a sudden it blasts if you're not using a good battery. So explosion is a big problem, but certainly lithium gives very nice results, but can be replaced. I would not say it is on research level, but can be replaced with magnesium, with sodium.
Thank you, ma'am. One more question.
Yeah.
One more question. There is a participant, Naina Sharma, is asking, ma'am, will there be any high power and long life batteries in near future?
Can be. For example, we are certainly there are many research groups working on the batteries, for sure. Many research groups working on the development of this, and certainly they have achieved few very good results using Na based batteries, and this hybrid systems will certainly solve this issue, which I mentioned in my presentation. Can solve this issue.
Thank you, ma'am. Any more questions, Chaya, ma'am?
Yes. Ma'am, there is a question from Ronit Makijani. Are there any side effects of this technology on our environment?
See, of course, if you're using certain kind of chemical, you need a disposable, right? So that's why, for instance, in my work, I'm using biomass kind of material, because carbon material is easily absorbed by our nature, right? We have a carbon cycle and can be easily absorbed by that. So of course, everything has disadvantages. Whenever you use chemical, there are disadvantages, but there are proper disposable methods also available for this. But it is also a harsh reality that now we cannot live without it. So we need it.
Thank you, ma'am.
Thank you, ma'am. The last question from Ria Ahuja. Can we have superconducting batteries to be used in a mobile in your future?
Yes, of course. Of course, there are few things which are already developed in terms of smart technologies. For example, nowadays, it's very, in near future, there is one possibility that you can wear your t-shirt, keep your mobile phone in the pocket of the t-shirt, and your phone is charged. So we are getting smarter and smarter.
Any more questions, madam?
No, ma'am.
No.
Thank you, ma'am. Thank you.
Thank you so much, Chaya madam, Romsha madam, and Dr. Amrita madam.
Thank you.
Now I would like to invite our collaborator EC member IAPT, Dr. P.K. Dubey sir, for his concluding remarks on today's topic.
I want to congratulate Dr. Amrita Jain, madam, for giving lot of information in a limited time. It's really is a very good topic, supercapacitor. Since I work in this field, capacitor, high voltage, power electronics, high voltage engineering. So I enjoyed the storing capacity of capacitor, how to shape the pulse and how to increase or decrease the rise time and so many things. Now we are having this capacitor in the range of 1 farad, I think so, madam.
Yes.
With low voltage.
Yes.
The voltage ratings are small. So if we are having capacitor of 1 farad, means the storing capacity is no doubt
It's super high.
Super high. It is eco-friendly. A new type of energy storage device. We are having, you explain this conventional capacitor and rechargeable battery. The most important thing in this talk is that you started with the basic capacitor. So this Indian Association of Physics Teachers is working basically for the upgradation of physics teaching and physics teachers. So we are trying that in our webinar, seminar, the basic things should be there. Fundamentals should be discussed. Means more and more fundamentals, 70% fundamentals, 30% research. So I find your lecture is a popular one. It's interesting.
Thank you. Thank you so
I
much.
congratulate so many information. And I also congratulate the management of this college, principal, vice principal, HOD, for selecting this nice subject. Now we are having so many webinars now these days. But to attract participants, the topic should be of current interest. This topic means no one can imagine that we are having a capacitor of 1 farad.
Yes.
It's very difficult to digest, but we are having it.
Yes.
So congratulations to Archana Srivastava madam, Galgale madam, and I'm also thankful for you using this IAPT platform. And IAPT means it is basically working for school students, school teachers, basic. So I found that it is this problems is there in college also, in university also. So these type of lectures, webinars are helpful. Now this we are having more than 1,000 participants. So I think it's broad spectrum will be there, from some belongs to school, college. So I think all will enjoy this your lecture. Thank you very much.
Thank you. Thank you so much.
Thank you so much, sir. Now I request HOD Physics Department, Dr. Jyotsna Galgale, madam, to propose formal vote of thanks.
Sairam.
Sairam.
On the behalf of Department of Physics, we feel great pleasure in expressing our deep sense of gratitude to our keynote speaker, Dr. Neeraj Gaur, and our subject expert, Dr. Amrita Jain, for inspiring and imparting their knowledge in an interesting and fascinating way. It was very insightful. We learned and enjoyed a lot. Thanks again. Thank you, Amrita.
Thank you.
We are indebted to the chairman, Dr. Meena Pimplapure, and the principal, Dr. Sudha Pathak, for their constant motivation and inspiring words. Also would like to thank Dr. Asha Agrawal for her advice and support. On this occasion, we are thankful to Dr. Pradeep Dubey and all the members of IAPT for their counsel to conduct this event. Not to forget, seamless technical support provided by our computer department. We are obliged to Mrs. Arpana, Mrs. Chaya, Dr. Romsha, Ms. Girjesh, and all the staff members for their contribution to conduct this webinar. A special mention and my immense appreciation to Dr. Archana for proactively initiating and organizing this webinar efficiently. Last but not the least, our heartfelt thanks to the participants from all over the world. Without your active participation, this venture would have not been a successful reality. Once again, thanks to each and everyone. Jai Hind, Jai Bharat. Saira.
Thank you so much, madam. Now, at the end, as the tradition of our institute, we are closing this ceremony with Mahamangal Aarti of Baba.
ओम जय जगदीश हरे स्वामी सत्य साई हरे भक्त जना संरक्षक पति महेश्वरा ओम जय जगदीश हरे शशिवदना श्रीकरा सर्वा प्राणपते स्वामी सर्वा प्राणपते आश्रित कल्पलतिका आपद बांधवा ओम जय जगदीश हरे मात पिता गुरुदैव मरि अंतयुनीवे स्वामी मरि अंतयुनीवे नाद ब्रह्म जगन्नाथ नागेन्द्रातयना ओम जय जगदीश हरे ओंकार रूप ओजस्वी ओ साई महादेवा सत्य साई महादेवा मंगल हारति अंधको मंदर गिरिधारी ओम जय जगदीश हरे नारायण नारायण ओम सत्य नारायण 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 ओम नारायण नारायण ओम सत्य नारायण नारायण ओम सत्य नारायण नारायण ओम जय सद्गुरुदेवा
Thank you so much, all of you.
Thank you, madam.
Thank you, sir.
Thank you.
Thank you, everyone. I hope it was a very useful webinar for all the participants.